So now that you know how to calculate the expected value and standard deviation, we can talk about some of the properties of those two functions, as well as the fact that we can create linear combinations of random variables. So we can actually create new random variables from the old variables that we already have. And so I'm going to go through the properties of the expectation and variance operators, and then I'm going to work through some problems so you can see it in action. The first rule has to do with addition and subtraction of a constant. This is similar to shifting data. So if you add or subtract a constant to every single observation of your data, you only shift it up or down, but you don't change the spread at all. And you guys maybe remember that from exam 1. This is similar. If you add or subtract a constant to every single outcome, then the expectation is going to change by that exact same constant. The spread doesn't change, however, so if you add or subtract a constant to every single outcome, the variance is going to remain the same, and that's what this here is stating. Division and multiplication are a little bit different. As we said with data in exam 1, if you divide or multiply by a constant, that changes the measures of position, but it also changes the spread. The same thing is true when we multiply each single outcome by the same constant. That's going to change our expectation by the same way in which we change the outcomes. But it also changes our spread. And the way it changes our spread, or our measure of variance, is that the constant actually gets squared, and this is because the variance is a squared function. So let's work through a few problems so you can see these two rules in action. Let's suppose we have two random variables, and I'm not even going to try to say what these variables are. They're just variable x and variable y. So the mean of x, that is our expectation. The standard deviation of x is just the standard deviation. And then we also have y. We want to find a linear combination of x, so we just want to find the mean and standard deviation of 3x. So the expectation of 3x can be written as 3 times the expectation of just x. And this is because we said multiplication and division constants can be taken out of that expectation operator. What this leaves us with is 3 times 60, because 60 is the expectation of x, so that gives us a final mean of 180. The next thing that we're going to calculate then is the standard deviation of 3x. And to do this, we have to go through the variance operator. Remember that the definition of the standard deviation is just the variance square rooted. And so we have to do this because the properties that I talked about before have to do with the variance operator and not the standard deviation. So we have to go back to the variance operator and find how these constants affect it, and then recalculate the standard deviation. So as we said before, multiplication of all the outcomes affects the spread of the variance. And so when we take that constant out of the operator, it gets squared. So 3 squared is just 9, and now we're left with 9 times the variance of x. Because these are multiplied under the square root operator, we can square root them separately. So the square root of 9 is 3, and then we're left with the square root of the variance of x. Now remember that the definition of the standard deviation is just the square root of the variance, so we're actually left with 3 times the standard deviation of x. And we know what the standard deviation of x is. That's given to us in the problem. That is 10. So the answer to this is 30. Now I want to point out a few things that tend to confuse people. When I use parentheses here, what I'm talking about is an operation or a function. I'm not talking about multiplying the square root times a variance or variance times 3x. What I'm saying is that 3x is entering into the function of a variance, and the variance is entering into the function of a square root. So the parentheses that I will use for the most part in these problems means that I'm dealing with a function. I'm not doing multiplication when I have these parentheses. That was a pretty easy problem. Let's move on to something a little bit more difficult that does both addition of a constant and multiplication of a constant. And we'll only focus on one random variable here. We'll focus on the random variable y. The expectation of this new variable, 3y plus 4, that's pretty intuitive to calculate because, again, our constants just come out of the expectation operators in the way that we would expect them. So it's going to be 3 times the expectation of y. The expectation of y is given to us in the problem. It is the mean of y. That's 10. And then we're going to add 4, and so our expectation of this new random variable is 34. Let's move on to doing the standard deviation of this random variable. Remember that the definition of the standard deviation is just the square root of the variance. And we have to focus on the variance again because our rules for addition and multiplication of the constants operate through this variance term and not the standard deviation. So we have to go back to the variance to determine how these constants affect the spread. Let's start with this constant that's added. Remember that adding and subtracting constants don't change the spread, and so our spread is going to be the same regardless of adding that 4. And so the final term is just going to be the square root of the variance of 3y. We can simply write it that way. And now our problem looks similar to the last one where we're just dealing with multiplication. So now when we take out that multiplied term out of the variance operator, it has to be squared because the variance is a squared term. And that means 3 squared is 9 times the variance of y. And because these are multiplied together, we can square root them individually. So the square root of 9 is 3, and the square root of the variance is just the standard deviation of y. So remember that the standard deviation of y is the square root of the variance. That is its definition. We're given the standard deviation of y in the problem. That's just 2, and so 3 times 2 is 6, and that's our final answer. So now that we know how to deal with constants, the addition and subtraction, multiplication, and division of constants with a random variable, let's move on to the linear combination of random variables. And what this means is that we're adding or we're subtracting 2 random variables together. And the rules for that, for the expectation operator, is that if you just add 2 random variables together, it's the same as adding their expectations together. For the variance operator, again, this is a little bit more complicated. If you add or subtract 2 random variables together, that variance of that new linear combination is going to be the sum of their variance. Now this is going to be important to note that even if you do subtraction, they're still adding the variances together. And so you can find the variance of the new random variable by just simply adding the 2 variances together. Let me give you a quick example of 2 random variables where we might add them together. So let's say we're interested in figuring out the sales from a coffee shop, and X is the sales from coffee and Y is the sale from donuts. And so we can figure out how much spread there is in total sales from coffee and donuts. And by just simply adding up the sales, the variance of the sales of coffee plus the variance of the sales of donuts to get the total variance of the total sales. In order to be able to do this, we have to make the assumption of independence. So what that means is that the sales of coffee don't affect the sales of donuts. That's a pretty strong assumption, but we're going to use that assumption for our problems because dealing with dependence is a lot more complicated. The way that you deal with dependence is through the covariance operator, and it looks like this, and it deals with the fact that those two variables may be related. But again, because this is much more complicated and requires much more math than we are focusing on in this class, we're going to assume that we're dealing with independent events for our problems. And so we can simply just add up those variants and not have to factor in the relationship between those two variables. So let's work through a few problems so you can see these random linear combinations of random variables in action. So the expectation operator is pretty straightforward and intuitive. You can simply plug in the expectation of x into where x is and the expectation of y into where y is because we're dealing with constants and we can simply add up those expectations, and so that's going to be an answer of 260. So let's move on to the standard deviation because that's what's a little bit more complicated. Remember that we have to go through the variance operator, and the definition of the standard deviation is just the square root of the variance. So we rewrite this in terms of the variance, and then what the next step is to deal with the fact that we have two random variables in our new linear combination of the variable. And so we want to separate those out, dealing with those variances individually, and we said that we can do that if we assume independence. So again, we can separate out x and y by assuming independence. The next step would then be to remove these constants of the 4 and the 2, and when we remove those constants, they get squared. So the square of 4 is 16, and squaring 2, that gives you 4. And so now we have the variance of x and the variance of y separated out. Next, the next step is a little bit more complicated because we want to get back to the standard deviation of y and the standard deviation of x. But we can no longer just square root things individually because the addition means that we can't just square root separately. We have to do the addition first. And so what that means is we have to deal with the fact that the variance is defined as the standard deviation squared. So I can rewrite this term in this way because the variance of x is just the standard deviation of x squared. So I'm only squaring the standard deviation. The same thing for y, I'm only squaring the standard deviation of y. And now that we have the standard deviations, we can go ahead and plug in what the problem gives us. We can go ahead and plug in 2 and 10. Now we've plugged in 2 and 10 into these appropriately standard deviation y and standard deviation of x. And then we're going to go ahead and multiply these terms first, then do the addition, and the last thing you want to do then is the square root. So you want to do the multiplication and addition first, and then the square root second. That's going to give us an answer of 40.2. So let's move on to another problem that's maybe a little bit more complicated. So here we have a new random variable that is a linear combination of two other random variables. But this time we're subtracting y from x, and so that's going to change things a little bit. When we find the expectation or the mean of this new random variable, it's intuitive like it was before. So we can simply take the constants out of those expectation operators and separate the expectation from the of x from the expectation of y, and that's going to give us an expectation for this new variable of 70. So that's pretty straightforward. It gets a little bit more complicated when we deal with the standard deviation. Again, we're going to have to go through the variance operator. So the definition of the standard deviation is just the square root of the variance. So that's just simply rewritten here. The next thing we want to do is we want to remove the random variables, separate them out underneath that square root term. So we can do that again when we assume independence. And so here I've separated out 2x from the variance of negative 5y. And I want to keep this negative term with its constant because that's what gives us this addition in the center here. And you're going to see why that's important in a second or two. So when we separate out those constants, keeping the negative term by itself, we can use our multiplication rule for the variance operator. And that rule is that when you bring the constant out of the variance operator, it gets squared. So 2 is getting squared to 4, negative 5 is getting squared to positive 25. And that's why when we deal with negative terms of linear combinations, those variances get added. So now we've got the variance of x and the variance of y separated out, but the problem gives us standard deviation of x and standard deviation of y. So we want to use the property that the variance is the standard deviation squared. So we can simply put in the standard deviation of x squared in place of the variance of x. And we can put the standard deviation of y squared in place of the variance of y. So that's what I've done in this step. The next step is then just to put in the standard deviation of x, 10, plug that in, and the standard deviation of y, I plug that in to the standard deviation of y. And that gives us a final answer of 22.36. Remember, when you do this square root, you want to do that last. So you want to do the addition of this first and then square root this final term last. So that's the basics behind how you do linear combinations of random variables. It's important to remember that the subtraction of one random variable from another holds for the expectation operator. But when you're dealing with the variance, that subtraction term gets removed, and it gets removed because that negative constant is getting squared. So what you do then is you just add up the variances rather than subtracting them. That's the important thing to remember for this variance operator. The other thing to remember is that these random variables have to be independent, and so we're assuming some independence between these two, and that's a strong assumption. Now that you've seen some of the functionality of these properties and basic problems of them, in the next set of videos I'm going to go over some word problems so you can see how they might be used.